Gradient descent today. So, as probably most of you are familiar with gradient descent, the main equation can be written as this. So, the value at x k plus 1. So, the value at k plus 1 equals xk minus sk gradient f of xk. So what are we trying to do here? We're trying to optimize for function f. Trying to optimize for f. And f is a function of x. So we start at some value xk, and then we keep updating that value xk plus 1, xk plus 2, and so forth iteratively until we arrive at some optimal point xk, x star, that minimizes f. So what we're trying to do is, for optimizing for f, we're trying to find the minimum fx, and we're trying to find x that minimizes this, right? So we write this argmin and minimize for x, right? All right, and what is sk here? This is the step size. So this is the size of the modification of value x depending on the gradient. All right, and this step size is very crucial in the convergence of this optimization process. So too large sk will result in oscillations, and too small an sk will take too much time, too much iterations. Now, the best way to perhaps find an optimal sk would be an exact line search on sk. And that would mean choose argmin sk with f xk plus 1 in the gradient f direction. So we have this direction. In this direction, we search for some point that corresponds to this sk value that gives the best f xk plus 1, right? And actually, it's often we can't solve for sk when considering exact line search, so we might again try to iteratively determine the best xk for the exact line search. Now, most of you who are familiar with gradient descent will know that exact line search is another problem on its own, so it is avoided often, and we just set some fixed value of xk. And those of you who are more familiar, especially with deep learning recent techniques, will know that recent techniques involving the step size often use decay, step size decay. So start with a large s so that it doesn't take too much iterations. It starts rapidly, it moves rapidly at the start, and when it gets closer to a convergence point, decay the sk value so that we can avoid oscillations. So step size decay, learning rate decay, as you will, what is this? You might be more familiar with learning rate, right? So step size is also called learning rate. So learning rate decay is a technique that is often used. And also, more recently, we have various schedulings of learning rate, right? So it can be scheduled to vary as following a cosine value or so forth. So there are various techniques of determining or trying to use a good step size. All right, so that's the basic of gradient descent. But in this lecture, we are trying to sort of analyze the convergence and the behavior of the gradient descent method, and particularly compare this vanilla gradient descent. So this is often just denoted as a vanilla gradient descent because that's the most basic. And then it is often modified to involve a momentum term, and this is actually accelerated gradient descent. And in this lecture, I will try to provide some analysis that shows insight into the different behaviors between the vanilla gradient descent and the accelerated gradient descent, particularly using an example. So let's go to the example. So now we have an example. So our example is the function. The function f is given as 1/2 x transpose sx. So this is a quadratic function, and here x is, the vector x is small x, small y, and the matrix S, let me denote this matrix as this, is a diagonal matrix 1, 0, 0, b, a very simple matrix. Then this quadratic equation becomes 1/2 x squared plus by squared. Now this, if we just write x squared plus y squared, what is this equation for? This is the equation of a circle, right? If we add this b constant, then the axes of the x and y directions, they might have different lengths, right? Then what does this equation represent? It becomes an ellipsoid, right? So this is an equation of an ellipsoid. Now, for this matrix S, what are its eigenvalues? Its eigenvalues are 1. Let me write them as lambda max and lambda min. And here we are assuming that b is smaller than 1. So lambda max is 1, lambda min is b. Now let me introduce a concept called the condition number. And this number should apply to all matrices because it's based on the maximum eigenvalue and the minimum eigenvalue. And here, so the condition number is the ratio between lambda max and lambda min. And here this is 1 over b. And this is all often denoted as kappa, Greek letter kappa. So here, because we have such a simple matrix S, this condition number is very easy to compute, but for more complex, more larger matrices, it might be more difficult to find. Now, as I mentioned, this function is a quadratic function that looks like a ellipse. So it has level set ellipses. So if we set this as some value r square, these kinds of ellipsoids will form with different r values that those different ellipsoids, the sizes of the ellipsoids would change. Now if we draw that graph in a three-dimensional form so that we have the function value as the third z dimension, then it looks like a bowl, right? With these convex, this convex shape and these ellipsoid level sets. So this level set would be a plane that is a plane intersection of this bowl would be a level set. So the ellipsoid is the intersection between the convex cup, the function, and some plane in the parallel to the xy plane, right? All right, we know that this value has its minimum value at x equals 0, and the function value should be 0. So we can write that arg min x fx is x star, and that x star is 0, 0. So this is like the most basic of quadratic functions. Very simple quadratic equation. But although we have this kind of simple function, we're not assuming, we're assuming that we don't know the x star, and we're going to apply gradient descent to this problem, to this function. So now let's compute the gradient for this function. So for f, so what is its partial derivative with respect to x? It's going to be is x, right? So the gradient, the partial derivative, 2x 1/2 is x, and the partial derivative with respect to y is by, right? So gradient f is x by. Now, if we insert this gradient f into the gradient descent equation here, then we get, so let's write the gradient equation. Why don't we erase this and then have this here, and then the gradient descent equation, xk plus 1 yk plus 1 equals xk yk minus step size k xk and byk. And then this is now we have to insert values for xk and yk. And why don't we start at b comma 1. So this is an example. This value has been set for illustrative purposes, and let's just assume that we start at b comma 1. So then we get b minus skb and 1 minus skb. Now here, as I mentioned, we can think of what kind of values that we are going to use for s. Let's assume we are using exact line search. Then we have to determine the optimal value for sk for this current situation, right? This is the xk plus 1 and yk plus 1. So given this xk plus 1, yk plus 1 value set to this, we are trying to determine the best sk that will minimize our function f. So we can insert these values, xk plus 1 into here and yk plus 1 into here, And then we will get, so f x k plus 1 is 1/2 b minus sk b squared plus b times 1 minus sk b squared. Now, we can rewrite this as b squared minus 2 sk b squared plus sk squared b squared plus b1 minus 2 skb plus sk squared b squared 1/2, and then this is 1/2. Now we have, so let's get the sk square terms. So for the sk square terms, sk square, we have b square and b cubed. And then for the sk terms, we have minus 2b squared and minus 2b squared. And for the constant terms, we have b squared plus b. Now, we have this equation, and because we're doing exact line search, we are going to differentiate f with respect to sk. Then this becomes, so we're differentiating this with respect to sk. So then what we get is 1/2 2 sk b squared plus b cubed plus minus 4 b squared. That's it, right? And this should be 0 for the optimum sk. So we get sk b squared plus b cubed and equals 2b squared, right? So 1/2 cancels this, and this moving to the right hand side, the signs cancel, and then we get sk equals b plus 1 and 2, right? So cancel the b squared terms, and we get 2 over b plus 1. Now, if we insert this value, 2 over b plus 1, in here, so then what does the xk plus 1 and yk plus 1 become? B minus b plus 1, 2 times b. So if we, so let's just first write for the xk, then we get b plus 1, b plus 1 minus 2b. Then this becomes b squared plus b minus 2b. So this just becomes b plus 1, b times b minus 1. Right? And for the, so this is xk plus 1. And similarly, we can write, so let me just make some room here. Let me move this a little below. And similarly, if we insert the b plus 1, 2 over b plus 1 into sk here, so here xk plus 1, so yk plus 1 becomes 1 minus b plus 1 to b, which is b plus 1, b plus 1 minus 2b. Then this becomes b plus 1 and 1 minus b. So it might be a bit easier to read if we write 1 plus b. So 1 minus b over 1 plus b is the yk plus 1. So we started at b plus 1. Xk was b and xyk was 1. And these values became xk plus 1 equals b times b plus 1, b minus 1 over b plus 1. And yk plus 1 became 1 minus b over 1 plus b. So these ratios have been multiplied to the original values. Now, if we assume that we can perform this exact line search for all k values, this ratio is going to be always common. So we can distill this. So let me just move this below further. And so here, then we can write xk is going to be the starting b. So now this is actually, the start is k equals 0, right? K equals 0. So when we're starting at k equals 0, the b, and then we have some any k value, then we can just write b minus 1 over b plus 1 to the power of k, and yk is also 1 minus b over 1 plus b to the power of k. So this kind of shows the equation for the change of the xk and yk values, and this can be combined to find the change of rate of the function for the different xk, yk values. And this can be written as 1 minus b over 1 plus b squared to the power of k times the initial function value. So this is just an illustrative example, but it shows that this is the rate of change for the iterations for the gradient descent method. All right, so let's keep this ratio in mind, especially when we are going to compare with the gradient descent that's accelerated using momentum. Now, before we move on, let me just remind you that our function is formed as ellipsoids, and I mentioned that the lambda max is 1, lambda min is b. Now, if b is very small, then we are going to have these very elongated ellipses. So b being small means that we have a large condition number. And if we have large condition number kappa being 1 over b, lambda max over lambda min. So if b is very small, and we're assuming b to be smaller than 1, the ellipsoids are going to be very elongated. And if we think of this kind of gradient value, we can see that for elongated ellipses, the gradient value looks to be very zigzaggy. So the worse the condition number is for this kind of problem, gradient descent might not work very well. We can see that also from this ratio. If we have a very small b, then 1 minus b over 1 plus b is almost 1, right? So we can see that with a quadratic problem with bad condition number, then we're going to have trouble with this vanilla gradient descent. Look at gradient descent with momentum. And this is accelerated gradient descent. Now, we can first start by noting that the rate of change that we just saw was 1 minus b over 1 plus b squared for gradient descent. This can change to, this will change to 1 minus root b over 1 plus root of b squared for GD with momentum for example. For the example that we are seeing, the illustrative example. Now, if b is 0.1, for example, then the GD gradient descent rate of change would be 0.99 over 1.01 squared, right? But for that same b, the rate of change for accelerated GD would be root b would be 0.1, not 0.01. So then it would be 0.9 over 1.1, which is much smaller than 0.99 over 1.01, and squared, then the difference would become even larger. So this is smaller. And if the rate of change is smaller, that means that convergence occurs faster, right? So this is better. So we can see that indeed the gradient descent with momentum accelerates the gradient descent. So that's what we will see. And let's look at the definition of gradient descent with momentum. So similar with gradient descent, we can start with xk plus 1 equals xk minus sk, this s being the step size. But here, now instead of the gradient, we will insert another term called zk. Now this zk is the memory term. And this zk is defined as the gradient at k corrected by or augmented with the memory of the previous memory term. So zk is the gradient together with memory. So what would be in the memory? So if we start with z0 and there is no prior memory, then we would start from just the gradient. But then, what would be z1? Then z1 would be the current gradient, and the current gradient combined with the previous gradient, right? So this would be sort of a combination of the gradients. Now, here the coefficient is negative beta, but because we're not constraining beta to be positive, I believe, so this can become the beta can be negative so that the memory and the gradient are added. I think this beta is a term that can be controlled just as this step size, as the portion of the memory within the momentum. All right, so now, in contrast to gradient descent only had k's and k plus 1 terms, but with GD with momentum, now we have terms for k plus 1, k, and k minus 1. So it's sort of similar to second order differential equations, in that there are three terms with different orders. Now, how do we deal with second order differential equations? We write them as a system of first order equations. So, similarly, we would want to write these two equations as a system of two first degree difference equations. So, the first equation we can write just the same as xk plus 1 equals xk minus sk. Let me omit the bracket and write as sk minus skzk. Now, and the second equation, we want all k plus 1 terms on the left-hand side, and preferably we only want k terms on the right-hand side. So in order to do that, we need to plug in k plus 1 instead of k and k minus 1. So if we insert k plus 1, we get z k plus 1. And since this k also has to be replaced to k plus 1, and we're trying to collect all the k plus 1 terms in the left-hand side, we need to move this gradient fk term to the left-hand side. So now we get gradient fk plus 1. And in the right-hand side, we only have minus, wait, I think this should be plus. Yeah, this was sort of strange. Yeah, I think that was an error on my part. So here, then, on the right-hand side, we just have beta zk minus 1, right? So I think it should have been, yeah, it's like this, okay. So, sorry. And we insert k plus 1 into k, so k plus 1 minus 1 is just k. All right, so we only have k plus 1 terms on the left-hand sides of the two equations, and we only have k terms in the right-hand side. Then, what can we do? We can convert this into a matrix. So here, we're converting this to a matrix, a system of equations represented in a matrix where this is xk plus 1, and then zk plus 1, and here we give xk and zk. Now on the left-hand side, for the top row, the first equation, we have on the left-hand side here 1xk minus sk here. And for simplification, let's just omit the k index with the step size. And then with the z, we have 0 and beta. And here in the left-hand side, we have 1, 0 for the top equation. And for the bottom equation, we have negative gradient fk. Sorry. So let me just first write negative gradient, and I'll explain why we can write this gradient as a coefficient of x, because this is a gradient of related to x with respect to x. So we could sort of write it like this. And then for the zk plus 1, we have 1 zk plus 1. Now, you should remember that we're comparing. So this rate of change with the b, this is related to all of this. Actually, this example. So we're still examining this example function, and we're replacing the gradient descent with the accelerated gradient descent. So to write it again once more, the example function f was 1/2 x transpose s x. Now, to avoid confusion with this step size, this is the step size in the gradient descent, and this is the coefficient matrix, symmetric matrix. One zero zero b. I will denote this S matrix with this symbol. All right, like this. Now, what is gradient f? Gradient f is Sx. We can see this as gradient x was, so 1/2 x squared plus by squared, right? And for this gradient, it was x by, right? And what is Sx? If we multiply s and x, then we get x and by, right? Just like this, right? So we can write the gradient like this. Then, what can we do? So we can insert this Sx instead of gradient fk plus 1, we can insert sxk plus 1, right? So we will write this, and then we can see here that we can write minus S matrix in the place of the gradient. Minus S matrix xk plus 1. That's this term, right? So now this is the full system of equations. Now, we are going to do one more thing. We are going to convert vectors xk and zk into convert. So let me rephrase. So we're going to convert the system of equations of vectors xk and zk into system of equations of scalars ck and dk. How are we going to do this? How? Use eigenvectors. So we're going to reframe the equations with respect to the eigenvectors. Now, how do we do that? So, because this is our target equation, so this is our target equation, right? And this is our main matrix. So our target equation, our main coefficient matrix. And we mentioned that this is a convex bowl in the xy plane. And for this kind of quadratic term, we have reviewed the concept of positive definiteness, right? And you can remember that on this convex bowl, the eigenvectors were the directions, the main directions for the ellipsoids, right? And for any tangent direction on that ellipsoid, we can think of the vector as being linear combinations of the two main eigenvectors. So we can think of the any vector xk as a linear combination of the eigenvectors. So if we have two eigenvectors, q1 and q2, so we can write xk equals ck1 q1 plus ck2 q2, sort of like this. Now, if we consider too many coefficients at once, it becomes a bit more complicated. So we would like to decompose these two eigenvectors. Just think of each eigenvector. And what is this eigenvector? This is the eigenvector of S. So eigenvector of S. We will denote as Q. So let's just think of one eigenvector. So let's write xk as ckq and zk as dkq. So we're just thinking of assuming that xk and zk only depend on the single eigenvector. Now, what is SQ? This is lambda q. This is the eigenvalue that corresponds to this eigenvector. Then, if we combine this equation with this equation, then we can write sxk as, so insert this into, plug in here, then we get, this is a scalar, so ck sq, which is ck lambda q, right? And then similarly, we can write, so xk plus 1 is ck plus 1 q, zk plus 1 is dk plus 1 q. So we can insert all of these terms into here, 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 and here. And these are all scalars, right? So they can just be themselves. So, or if we go back here, xk, so let me write this again. What is this? So this equation here, we can rewrite as ck plus 1 q equals ckq minus sk dkq, and then dk plus 1 dk plus 1 q minus sxk plus 1 is ck plus 1 lambda q equals beta dk q. Now, for both equations, q is the common factor for the left and right hand sides. So divide all equations by q. We can cancel q from every term. Now, this equation here, this equation, we can rewrite as ck plus 1, dk plus 1, and we have a matrix here, equals, we have another matrix, and ck dk. Now ck1 minus sk for dk here for the top equation, and then 0 beta for the bottom equation, and 1 0 for the top equation, and minus lambda and 1 for the bottom equation. So almost same matrix, 1 0. Now minus s has turned into minus lambda and 1 minus s. So I forgot, we are omitting the subscript k for the step size. We're assuming constant step size. All right, so s and 0 beta. This matrix is the same. So this is the updated equation, and we can find the inverse of this matrix very easily because this is an elementary matrix, a lower triangular matrix with all diagonal values 1. So its inverse is just the sign reversal of the off-diagonal element. So we can rewrite ck plus 1, dk plus 1 as 1, 0, lambda 1 times 1 minus step size 0 beta and ck dk. And we can combine this matrix and denote it as R. So R ck dk. Now, what we want to do is we want to find R within our accelerated gradient descent, these are our parameters. So these are our parameters of the accelerated gradient descent. Now we want to determine S and beta, but with what kind of criterion? The criterion is we want this to have a very fast convergence. So this power matrix must shrink ck/dk smaller and smaller faster. And do you remember if we write a to the 100, a to the power of 100, and if we could decompose a as if a is, I think it was as equals s lambda, right? So then a equals s lambda s inverse, and the s's are the matrices of the eigenvectors, and lambda is the diagonal matrix with all eigenvalues. Then it was this 100 power can be written like this, right? So the powers of a matrix can be controlled by its eigenvalues. So for this power matrix, we want it to shrink fast, which means we want eigenvalues of R to be small. More precisely, we want the maximum eigenvalue of R to be as small as possible. So we want how should I write it? We want to find the argument values that minimize the maximum of the two eigenvalues among E1 and E2 of the matrix R. And we want to determine the argument values for step size and memory coefficient beta. Step size S and memory coefficient beta. And one thing we can remember is here there's a lambda. So this R matrix depends not only on S and beta, but eigenvalue lambda. So R depends on lambda, which is the eigenvalue of S, the matrix S from the function. Now, this lambda we know should be between lambda is smaller or equal to large M and larger or equal to small m, which are m is the lower bound of lambda of S, large M is the upper bound, and large M over small m is the condition number of S. All right. So, given this problem, so this is the main problem. This is the current problem that we have, and our constraint is that the lambda value is constrained like this. And I'm not going to show the details of the solution, but if we solve this argmin for this matrix R, then we can find the optimal S. So the optimal step size can be determined probably fairly similar to the process where I determine the optimal step size for the exact line search that we saw for the gradient descent. So here, I'm omitting the process to obtain these values, but the S for the argument here, S optimal, can be found to be 2 over large M plus root of large M plus root of small m squared. And beta optimal is root of large M minus root of small m and over root of large M plus root of small m, again, squared. Now, fortunately, we have a very simple matrix S where this is B and this is 1. So we can immediately rewrite this as 2 over 1 plus root B squared, and this to be 1 minus root B over 1 plus root B squared, right? So we can see that these S optimal and beta optimal are the solution for the optimal values of S and beta, and for this value, we can determine the rate of change as mentioned to be this. So 1 minus root b over 1 plus root b, which is actually seen for this beta. So again, the rate of change at each iteration for the accelerated gradient descent becomes 1 minus root b over 1 plus root b squared for our example. So as I said before, this is an illustrative example showing the difference between the gradient descent vanilla style and the gradient descent with momentum. And it just describes how the momentum can be used to accelerate the convergence, so decreasing the rate of change for each iteration for the xk and xk plus 1. As you would expect, we can derive this for this simple expression, simple function, but it might be difficult to analyze, to do a similar analysis on more difficult, more complicated functions. But I think the mathematical intuition is valuable for understanding the process of the gradient descent and the gradient descent with momentum. So if we look again here, for the gradient descent, there was only one equation, but now there's a system of equations, and there's this matrix R that arises, and there are actually two parameters, and we can set these two parameters well, then the rate of change can be decreased like this. All right, so that is our discussion on gradient descent and gradient descent with momentum. And as again, I'd like to mention that this analysis has probably some differences, or its context is very different from what you might be familiar with if you have learned about momentum based on just the deep learning context. So this is more of a mathematical example analysis based on actually this function of the quadratic function of the convex optimization. So within the context of convex optimization, we can examine an example of gradient descent and gradient descent with momentum, accelerated gradient descent. All right, so please remember that. And remember that these values of S optimal and beta optimal should be plugged in here to get this optimal rate of convergence for this gradient descent with momentum. All right, so that will be all for today's lecture. See you next time.